Okay, we're going to take a look at the graphs of exponential functions, and we'll start off with this problem right here. It says a person knows a rumor. The next day he tells two people. The day after that, two people that he told the rumor to each tell two people, and the process continues for 7 days. How many new people know the rumor on the 7th day, and how many people total know the rumor? Write a function that gives the number of new people that know the rumor in terms of the number of days. Okay, so let's take a look at it. On the first day, you're the only one person that knows the rumor, and the total is 1. On day 2, 2 new people know the rumor, and that makes the total 3. The 2 new people plus you. 2 plus 1, 3. The next day, that doubles to 4, and if you add the 4 onto the 3, you get 7. Next day, it doubles again to 8, 16, 32, 64. So we could do it by hand here and get this, and get on day 7 a total of new people that know the rumor is 64, and if you would add up these as you go, you would get up to 127 total people. Now, the formula for these is this right here, n equals 2 to the t minus 1. This is an exponential function because the variable t is up in the exponent. We can see this here that it works. Like, for example, if I plug in, let's say, day 3. If I put 3 in for t, 3 minus 1 is 2, and 2 squared is 4, and that's what we have right there. Now, we can graph these exponential functions on the sheet right here called EXP, which is for exponential. This will only graph certain ones in this form, AE to the BX, where E is that exponential number, 2.718, and so on. So these you'll only see occasionally, and also we'll do curve fitting in that form. But you can only use this if the base is E. The problem that we want to graph has the base of 2. So if you scroll to the right, you'll see that we can graph any of them in this form. Now the base on this problem, we're looking at graphing again 2 to the t minus 1. So the base underneath that exponent is 2. So the b right here is 2. The a, we can think of that as being 1, because we can think of this right here as being 1 times 2 to the t minus 1. So continuing on, the number in front of that t up there is 1. We have 1t. So the c is a 1. There was no constant up there, and there also was no constant at the end. So there is the graph of this function right here. We could do it by plotting points as well, put in one number at a time through this thing to plot it. But and we could put in one number at a time here too. Like when we put 1 in, we got 2. When you put 2 in, you get 4, and so on. Actually, I do think it was t minus 1. Let's go back here and take a look. I think right here it was t minus 1. So the d, so we do have a value right here for d of minus 1. So now we can get the same values we got on that table there. Day 2, there was day 3, there was 4, and if you check that on the table, day 3, there was 4. Now this is an exponential function. You'll see that exponential functions have horizontal asymptotes on one side or the other. This one has a horizontal asymptote on the left. This is called exponential growth because as time, the x-axis, goes on, it's growing off to infinity. It's going off to infinity like this. On the left-hand side, the limit as x approaches negative infinity would be 0 because it has a horizontal asymptote at 0. Turns out that the horizontal asymptote on these functions is at the location of the f, the constant at the end. This one does not have a constant at the end, or a constant of 0, you could say. So that's why the horizontal asymptote is on the left at 0. Now, the function that describes the total number of people is this one right here, 2 raised to the t minus 1. Like, for example, to get this 15 total number of people that know this rumor on day 4, you would put 4 in here. 2 to the 4th is 16, and 16 minus 1 is 15. And let's go ahead and graph this one. 2 to the t minus 1. So it would be 1 times 2 to the t. No minus 1 there, but the minus 1 was out here. So if I put a minus 1 right here, you get a graph that looks like this. And plus we would get the values here. You could put in an x to get a y, or put in a y to get an x. Now, Notice it still has a horizontal asymptote on the left, but it's not at 0. See, here's 0 right here. This is leveling off at this height right here of -1. And you can tell it real quick by looking at this right here, that -1. Okay, just some other things on the graphs. This is again called an exponential growth. Exponential growth. And let me just delete a couple things here to make it a real basic function here. So this is y equals 2 to the x right here, because this is y equals 1 times 2 is 2 to the 1 times x is x. 2 to the x is what this function is. If I was going to graph 2 to the negative x, then I would have to put the value for c there would have to be -1. And if I take a look at that, the function goes like this. This is called exponential decay, because as time goes on, the amount is decaying down to a set level, the horizontal asymptote. The horizontal asymptote on this problem would be 0. The f is 0, and you can see it's leading off to 0. Or you can put in a large number in here for x, and this number here is very close to 0 because the capital E means times 10 to the -31st. In other words, you'd move your decimal point 31 place to the left. It'd be 0.0000, a whole bunch of zeros. And so very, very close to 0. So the horizontal asymptote is on the right. So the limit as x approaches infinity on this problem would be 0. The limit as x approaches -infinity would actually be infinity, because it keeps on going up on this side. So that's what this function looks like. And again, you can solve these by putting in a value for y right here. Like if we want to know when will this have a value of 64, here it is, -6. So if I look back here at this graph, back at -6, I'll see it as a height here of 64. So let's see what else we got here on these problems. So this is what I was doing, graphing exponential functions like this. And this is showing how you would do it if you put in values and did it by hand. If you put -3 in here, 2 to the -3rd, that means 1 over 2 to the 3rd, because a negative exponent means to reciprocate it, which would be 1 over 8. Put a -2 in, 2 to the -2nd would be 1 over 2 squared, or 1/4, and so on. And when you plot these points, you'll get the same graph as what I showed earlier, this exponential growth function right here. And this is showing the same sheet that we're using right here to graph these. That's doing both of them. 3 to the -x, this is a negative right here, so this is going to be exponential decay. Or you can put in the values and see what you get. Like for example, when you put -3 in here for x, the negative of -3 is 3, and 3 to the 3rd is 27. And when you plot these points, you get the exponential decay. So the function is decaying. The limit as x approaches infinity would be 0 on that. So in general, here's what these things do. The number on the outside gives you the location of the vertical asymptote. So if you have a function like this, y equals 2 to the x plus b, the plus b is down here at the same level of the 2, not up in the exponent, then it's going to have a horizontal asymptote at b. This one has a horizontal asymptote at 0, this one at 1, this one at 3, this one at -1, this one at -3. What happens when it's in parentheses and it's up in the exponent is that's a horizontal shift. Like this, y equals 2 to the x plus a. If you set that equal to 0, you'll get x equals -a. That means that the graph has been shifted to the left a units. This has no shift. This, if you set it equal to 0, you get -1. So in other words, it's shifted to the left 1 unit. This, you get -3, shifted to the left 3 units. This one, when you set this equal to 0, you get 1. That means it's shifted to the right 1 unit. And this one, x minus 3, if you set that equal to 0, you get 3. Means it's been shifted to the right 3 units. And that's pretty much your graphs of exponential functions right there. If it's something messy like this, remember to set the whole thing up there equal to 0. So you would set the -2x plus 1 equal to 0 and solve it, and that will tell you your horizontal shift. There's no vertical shift on this one because there's no shift up or down, so the horizontal asymptote would be at 0. Is it growing or decaying? Well, look at the coefficient in front of the x. It's negative. That means it's exponential decay. Exponential decay comes down and levels off on the right. So the limit as x approaches infinity would be whatever the horizontal asymptote is and for this one it's 0. So the limit as x approaches infinity would be 0. On the left-hand side, it's approaching infinity. So that's pretty much it with the graphs of exponential functions. And again, if you have to graph anything with an e in it, and we'll see this in later videos, this tells you right here how you type the base of e in there. You type in equals exp of 1. I'll do that here. Equals exp parentheses 1 close parentheses. And there's your number e for if you ever need it. So I'll stop right